Hello everyone. My name is Sanjay Dwarakanath, one of the faculty in Anesthesiology at University of Kentucky College of Medicine. In this lecture, I will present the basics of statistics that will help you prepare for your exam. We will go over some of the important basics such as understanding the data sets, the utility of some of the statistical tests that we use, where to apply, and why do we use it, and so forth. I would like to warn you that the tone of my voice will probably change as we go along in this presentation, mostly because the slides were recorded on two different computers at different time intervals, so please bear with me. One of the most important aspects of statistics is our ability to recognize the type of data that we collect. And it's very important to know so that we can assign these data to the correct types, which will allow us to use the appropriate statistical method to analyze these data. Broadly speaking, you can divide these data into two types: interval data and categorical data. And with the interval data, as the name suggests, the difference between the two data sets are equal. And in a categorical subtype, once again, as the name suggests, you assign the data to a specific category. Coming back to the interval data, it can be further subdivided into discrete or continuous. With the discrete data, the data is often measured as an integer. A good example is the number of teeth that the patient may have. On the other hand, a continuous data is, as the name suggests, it's continuous. A good example is blood pressure or temperature. And the data is oftentimes measured over a fraction or a decimal. Temperature of a patient may be 36.3, for example. Coming to the categorical data, it can be subdivided into dichotomous data, nominal, and ordinal. Dichotomous data is essentially two or binary data. A very good example is gender, male or female. With nominal data, you're assigning a characteristic of a patient or the data to a specific category. A good example is eye color. And all these data are qualitative data. Another example is, let's say you're doing a study with the physician subgroup and you want to identify what specialty is each physician under. The last type under the categorical data is ordinal data. In here, the data are put in a certain rank or measured without any scale. A good example is the ACE status or Mallampati score, where you have 1, 2, 3, and 4, but they are not necessarily measured with a scale. Descriptive statistics allows us a way to summarize the information. And the two most common ways to summarize a given set of data is by reporting their central location and variability. Central location will give you an idea of where most of the data is concentrated. And this is a very basic statistics that you all probably know. The three most common ways to report central location is mean, median, and mode. Mean is simply the sum of all data points divided by the number of data points. Median is the middlemost number. Mode is the most frequently repeated number. Variability gives you an idea of the spread of the data points. And the most common way to report it is either by variance, or even more common is standard deviation. And the formula is given in the bottom right. As you see, the formula, it is essentially the difference of each data point from the mean, and then you square it and you divide it by the total number, and the square root gives you the deviation, whereas the variance is without the square root. Statistical theory demonstrates that if the denominator or the divisor in the formula is n minus 1 rather than n, the sample variance is an unbiased estimator of the actual population variance. If the distribution of the data is normal, then it is important to know that one standard deviation would mean 68% of the data around the sample mean, and 2 standard deviation is 95% of the sample mean, and 3 standard deviation would be 99% of the data around the sample mean. Every research starts with an intuitive feel for the phenomenon to be studied. We call this the biologic hypothesis, which could be explicit or not. As an example, the intuitive feel may be, does isoflurane produce less myocardial ischemia? With this, then, we move on to establishing a statistical hypothesis where we select a parameter, or in other words, a variable, that will either help prove or disprove the biologic hypothesis. And in this given example, we can look at the ST segment changes with the administration of isoflurane. Hence, this becomes the statistical hypothesis. Once a hypothesis is formulated, it is very important to understand the errors in accepting or rejecting the hypothesis. Let us consider an example of an experiment which was conducted to observe the effect of remifentanil and sufentanil on decreasing the blood pressure. Now, accepting this null hypothesis would mean that there was no difference in the effect of remifentanil or sufentanil in decreasing the blood pressure. Rejecting the null hypothesis would mean that there is a difference in the amount of blood pressure decrease between remifentanil and sufentanil. So if you look at this table, let's assume the actual reality of the experiment is that remifentanil and sufentanil are equivalent in reducing blood pressure. On the left hand side, you can see the conclusion from your experiment. And let's say you do conclude that remifentanil and sufentanil are equivalent. In other words, we are talking about option A, or the box A here. Then you have correctly accepted the null hypothesis. On the other hand, look at the box B. The actual reality is that remifentanil and sufentanil are equivalent. However, you're rejecting that null hypothesis. In other words, you're saying that they are not equivalent. In this scenario, you have committed a type 1 error, also called as alpha error. Now look at the box C. In this instance, the actual reality is that the remifentanil and sufentanil are not equivalent. In other words, one of the medication is causing more decrease in the blood pressure. However, if you accept the null hypothesis, or in other words, you are saying that no, they are not really different, then that means you're creating a type 2 error, also called as beta error. In other words, you are not able to detect the difference between remifentanil and sufentanil. And lastly, look at the box D. In this situation, the actual reality is that remifentanil and sufentanil are not equivalent, and you did identify it correctly that they are not equivalent. So I hope that explains, or at least will give you an idea of what is alpha error and beta error. A typical value for alpha error is 0.05. what it means is, assuming that there is no difference between remifentanil and sufentanil, and let's say you conducted this experiment 100 times to see if there's any difference, then only during 5 out of those 100 times you will by mistake conclude that there is a difference. 95% of the times you will be able to correctly conclude that there is no difference. With the beta error, we saw that it's an error that we commit when we accept the null hypothesis, or in other words, we are not able to detect the difference. The power of a test is simply 1 minus beta error. In other words, what it is telling us is our ability to detect a difference between sufentanil and remifentanil in decreasing the heart rate. Now let's look at some of the tests we can utilize to analyze interval data. As we saw from the previous slides, interval data consists of either discrete variables or continuous variables, and typically parametric tests are usually the choice in the analysis of these interval data. An important assumption that you need to keep in mind is that the sample that is being studied should be drawn from a population that has a normal distribution. And as you all probably know, a normal distribution is a standard bell-shaped curve, as depicted in the picture in the bottom of the slide. T-test statistics was created or introduced in the 20th century, and this allowed the testing of hypotheses when the population variance was not known. The most common use of t-test is to compare the mean values of two populations. Let's take an example of an experiment where you administered sufentanil to look at the change in the heart rate. And let's say 2 sets of measurement was taken, one set of heart rates before sufentanil was administered and another set after administering sufentanil. So now you have 2 data sets from the same patient. In this situation, we use a paired t-test to compare the means of these 2 data sets that are coming from the same patient. So the pairing of measurements in this instance reduces the variability and increases the statistical power of the test. So that is one application of paired t-test. The other t-test is the unpaired or 2-sample t-test. Let's take a different example where one group received sufentanil, another group received a control medication, which was not sufentanil. And now you want to compare the heart rate between these 2 groups. Now these 2 groups are different set of groups. It's not the same individual themselves. So in this instance, you use unpaired or 2-sample t-test to compare the means of these 2 groups. Oftentimes during an experiment, you may have more than 2 sets of data that you want to compare with. Let's take an example of an experiment where you assessed the right ventricle function during various phases of a thoracic surgery, let's say lobectomy. Let's assume you looked at the right ventricle function before induction, and then at the second time you assessed the right ventricle function during 2-lung ventilation. The third time you assessed the right ventricle function during 1-lung ventilation, and you took a final assessment after the lobectomy. So now you have 4 sets of data. One way to do it is use the t-test and compare the set A, the data set A, with the means of the set B, C, and D, and then compare the mean of the data set B with the means of the data set A, C, D, and so on and so forth with t-tests. This is a very inappropriate use of statistics in this situation. The problem here is when you use many t-tests, the error rate keeps adding up and you're setting up yourself for a type 1 or an alpha error. Now remember that type 1 error or an alpha error is when you conclude that there is a difference between the means, even though there is no difference between the two means. The best approach to handle comparisons of means between more than two groups is the use of analysis of variance. In short, it's called ANOVA. The details of computing and deriving the results are probably a little bit beyond the scope of today's lecture. In this slide, I would like to touch base upon confidence interval and standard error of mean. Confidence interval is more like how likely is the mean of your particular sample to be the real true mean of the population from which you sampled. On the other hand, standard error of mean is more of a precision factor. The formula given is very important for your tests. As you see there, standard error of mean is simply calculated by dividing the standard deviation by the square root of the sample size. The way you should look at it is that standard deviation measures the amount of variability or a dispersion from the individual data values to the mean. On the other hand, standard error of mean really measures how much discrepancy there is likely to be in your sample's mean compared to the population mean. We talked about analysis of interval data using tests such as unpaired t-test, paired t-test, analysis of variance, etc. These tests are called parametric tests because they assume that the distribution of data in the population follows a bell-shaped curve, or in other words, we call it normal distribution. You can see a picture of that on the right-hand side of the slide. But what should the experimenter do if the data are not normally distributed? In these instances, we use non-parametric tests, where you don't want to assume that the data is normally distributed. Take an example of a data such as gender. There's only two options, male or female. There's no way it can follow a normal distribution. If anything, it will be a rectangular kind of distribution. And so is the ASA status. In the slide at the bottom, there's a table which lists some of the non-parametric tests and their equivalent parametric tests. Having said all of these, I would like to point out one important thing, that the experimenter can choose to ignore the problem of non-normal data and still use a parametric statistics for analyzing a non-normal distribution. And that is not unreasonable. However, for the purpose of exam, I would suggest that you pick a choice of non-parametric test when the data is not normal. Parametric tests are very robust in terms of their statistical analysis. In fact, they're also called as robust statistics. Categorical data, as we discussed in the previous slide, does not follow a normal distribution. We talked about an example of gender and ASA status already. Hence, in these data sets, we need to use non-parametric tests. And remember that categorical data is subdivided into dichotomous data, nominal data, or ordinal data. In this table, you will see a list of some of the tests that you can use depending on the nature of the data. So this is kind of like a summary slide. As we discussed, interval data, which can be continuous or discrete, oftentimes follow a normal shaped distribution in the population, and hence you can use parametric tests such as paired t-test, unpaired t-test, or analysis of variance. Categorical data, which can be either dichotomous or nominal or ordinal data, will probably need a non-parametric test, and some of those are chi-square test, Fisher test, and other non-parametric tests as listed in this table. This slide will help you understand the concept of sensitivity and specificity. Let's take an example of us trying to find out who has COVID in the given sample of population. The table on the left-hand side gives you the data of all the patients who have disease and who do not have disease compared to the results of the test that we conducted. The sensitivity of a clinical test refers to the ability of the test to correctly identify those patients with the disease. So in this given table, those patients with disease are A plus C. And out of those A plus C, the test correctly identified the number of positive people as A. So the sensitivity of this test is A divided by A plus C. Typically, a screening test should be highly sensitive, or its ability to pick up those patients with disease should be very high. On the other hand, a specificity of a test is its ability to pick up patients who do not have disease, or those who are negative for the disease. So in this given example, the specificity of a test is the true negatives, which is D, divided by those who do not have disease, which is B plus D. And then we also need to understand the positive predictive value and negative predictive value of a test. A positive predictive value of a test is how likely is it that this patient has the disease given that the test is now positive. And that is very easy. It's simply true positive, which is A, divided by all the positive tests, which is A plus B. And on the other hand, we have to understand a negative predictive value of the test, which answers the question, how likely is that this patient does not have the disease given that the test result is negative. So once again, the answer is very simple. It is true negative, which is D, divided by the total number of negatives, which is C plus D. I hope that will help you understand the concept. Thank you for listening to this lecture. This is a list of some of the keywords we covered so far with this lecture. Please feel free to find me if we can discuss something more, or if you find any errors in this lecture. And good luck to everyone.